Let's take a look at our options in terms of pumps handling clear water. End suction pumps, basically we've described a little bit. You've got a shaft which has two bearings on it. The one at the right-hand side is fixed. The one on the left-hand side can move axially to allow for thermal expansion. The reason and also that's the bearing that's taking the radial thrust. The other bearing on this one shows like a double row, and that's because occasionally these pumps are driven with pulleys. And in those cases, mechanically, a lot of side thrust is produced by the pulley and belt system. There's two basic arrangements, frame mount where the pump is supported onto itself and is connected by a coupling to a motor and mounted on a base, or close coupled where it's actually an extension of the motor shaft, special motor shaft that has provision for the seal and the impeller and all that good stuff. Performance curves, and there's factors that affect the design of it, but again comes from the manufacturer. Flow range, depending on the mechanical structure of the pump, the tougher it is, the more it can tolerate. Inlet, again, determined by inlet I and operating speed. So NPSHR is something you need to get from the pump curve, manufacturer's curve. Venting, if the discharge is straight tangential, you can get air trapped at the top of the casing. This one here, as you see, is what we call a centerline discharge, and the discharge is vertically in line with the inlet. That will vent any air that's in the casing and then just vent it off the discharge. Also, the casing has, you notice, feet on the bottom. Although these pumps aren't supposed to have external piping loads of any significance on them, the fact is that any downward load on the discharge flange will be transmitted through the casing to the feet to the foundation, so they're much more tolerant of that situation. Radial thrust is inherent in the design. It can, we mentioned, can be mitigated to a point by using double wear rings and a vented hub. Axial thrust, it's axial thrust that can be mitigated by having the rear wear ring and what hub. Okay, sorry for that. Footprint. This is dependent on the type of pump. Conventional frame mount pumps can be quite long. Close coupled pumps are more compact, and inline very compact. Inline is essentially a close coupled pump with a special casing that has an inlet that does a little snake into it, okay? Now, the only thing is you get into servicing, and the easiest to service is a basic frame mount pump, but with a spacer coupling. What that is you can see you can remove the coupling so that there's a gap between the pump shaft and the motor shaft. That allows you to undo the casing bolts, slide the unit back, angle it slightly, and remove the frame and impeller and everything for easy servicing and put it back. Now, it does add a few inches to the overall length, but well worth it. If you don't have that, you're going to run into a problem. You might as well, you're going to have to move the motor, etc., and maybe even some piping. Now, close coupled pumps are not as easy to service because the motor does have to be removed to pull the thing apart. An inline, same kind of deal, and they're somewhat limited as to what you can get in terms of inline pumps. ANSI B17 or 73.1 dimension pumps are intended for industrial process service, and they have very heavy-duty shafts and oil lubricated bearings. In other words, they are built. They can be used for pumping water heads up, and you can get some very high head units that work fairly well if you want to insist on an end suction pump. Note the shafts on these things are screwed on, and warning, with any pump having threaded impeller attachment or threaded shaft coupling, confirm correct motor rotation before coupling. Ask me how I know, because damage will result if the motor rotation is wrong and unscrews the shafting. Okay? Now, double suction split case pumps essentially are like two end suction impellers back to back on a single impeller and that has a horizontal split so you can pull it apart for servicing. Axial thrust is largely canceled because you're coming from two sides, and radial thrust is better tolerated because, as you can see with the red arrows in the center drawing, Um, the shafting is supported between two bearings, not cantilevered off the end. You can get double volute versions, and we'll explain that later, to cut back on axial, or pardon me, radial thrust, but again, it's costly. The performance curve tends to be rather flat because basically it's like two end suction pumps in parallel, okay? Because of that flat curve, they are ideal for systems where you're pumping into a flat area where you want just a constant pressure and you're not pumping into a reservoir or whatever. The flat curve also makes them ideal for fire pumps. NFPA, National Fire Protection Association 20, gets into double suction split case. The spec reads, the shutoff head shall not exceed 140 foot of the rated head. Pumps shall furnish not less than 150% of rated capacity at not less than 65% of total rated head. What they're defining is a flat curve, and these types of pumps will usually provide that, or can provide that. Since the impeller, again, we talked about being supported, NPSH depends on how they're done. The one thing is, of course, the flow is designed to come in and split on either side of the pump, and we'll get into that in a little more detail. The venting has to be vented from the top of the casing, and is critical. Can be done with a manual cock, or better yet, a small automatic air release valve, and we'll get into those later on. Radial thrust, again, is inherent, but it's supported by two bearings, and you get around. There is a double volute shown, and you can see the volute starts opposite the regular cut water, has its own system that comes down. They are a little rare and costly. Axial thrust, if the inlet is done properly, is a non-issue. But if you have an elbow on it, then what happens is the flow will not be split evenly between the two inlets. If you look in the center there, you can see that what would be the outside of the elbow tends to load the impeller on that side, or the half of the impeller on that side, quite heavily, and you will get axial thrust, what would be down on the, as it's drawn here. That can be significant. How it shows up is the thrust bearing is taking a whole lot of thrust, and it can get quite hot. So it is definitely not recommended. If you have to do an inlet like that with an elbow, you should have at least, according to NFPA 20, about 10 diameters in between. There's other ways of doing it. We'll get into it later in station design. Okay. The footprint, the basic footprint is fairly large, but you don't need a spacer coupling. You can get versions where the pump is mounted vertically. The problem with those is twofold. Number one, they are bare to service. When you pull that casing off, you've got the whole weight of it right now, and you can't just easily lift it off. And putting it back on can be a little tricky. Secondly, any water leakage will tend to go into the bottom bearing. So not recommended to go that route. Now, war story. Working for a pump supplier, it turns out that an engine-driven double suction split case pump had the wrong rotation. The inlet being where the discharge should be. I remember the contractor phoned up and he got the wrong pump. Instead of a 6x5, you've given us a 5x6. In other words, 5-inch inlets. Manufacturers don't do that. They may be equal, but if there's a difference, the bigger one will always be the inlet. So it turns out what happened was the manufacturer's shop drawings showing rotation from the outer bearing head differently than what Hydraulic Institute does. Bad manufacturer. And the engineer didn't catch that, so he approved it. Now, as it turns out, virtually any double suction split case pump can have the rotation reversed by disassembling the pump, reversing the impeller on the shaft, and then reassembling. However, it turned out that the engine involved had only one rotation, counterclockwise viewed from output, which is common worldwide. So there was only one rotation for that engine, and they had it. After much discussion, I suggested to a senior partner of the engineering firm that a solution would be to mount the pump upside down. Servicing would be difficult, but it's a standby fire pump, so probably ain't going to be serviced very much, if ever. In all other regards, the pump would be happy. This drew a rather angry response, comment being, well, here we have this serious problem and you're coming up with nonsense like that, and he was quite upset. The next day, I get a phone call from the same gentleman saying they have reconsidered my stupid suggestion and were proceeding accordingly. Now, what I was talking about, if you look at this drawing, there's the typical, inlet on the left, discharge on the right. Again, a 6x5, uh, and that's rotation would be counterclockwise. But unfortunately, that view on this one is from the shaft end, but the other one, the manufacturer's drawing showed it from opposite the shaft end. So they had the wrong rotation and had approved it. So what do they do now, given the engine? Basically, if you take that pump and just simply rotate it around the shaft, you then have the suction on the right-hand side, the discharge on the left-hand side, okay? All you have to do is mount the pump sturdily, and so you can get at it, and have venting on the pipelines, okay? This, unfortunately, is a photocopy of a picture. That's the closest I ever got. There is the actual pump mounted upside down, and you can see the frame they built. I think I'd have made it a little more open to make accessibility there, but whatever it is, it worked. They were happy. On a similar vein, once upon a time, the GM diesel, Detroit diesels were two-stroke, and getting opposite rotation was just simply a case of asking for it. And this is kind of an oddball but interesting application where the two pumps had opposite rotation and the engines had opposite rotation. And as you can see, the inlets came up and then there was a common discharge down the center. Now, boom, I put in fireworks, vertical turbine pumps, because they're one of those subjects that usually get a reaction. For example, Metro Vancouver uh, does not want vertical turbine pumps, and I can appreciate why, because there's the systems they got are fairly flat, and vertical turbines are not the easiest thing to service. However, they do have a lot of advantages as well. They're easily staged, so you can get high heads and whatever. Uh, and they're pump people like them because they're sort of built component by component, and there are games you can play with them. Now, typically vertical turbine pumps, not all, but most of the impellers offered will be Francis type. In other words, they're gunning for that 2300 specific speed because that gives you the most efficient pump. And what do you do if you need more head? You add stages. Now, there is the typical pump. You've got a high thrust motor at the top because the impellers will give you axial thrust down, and it can be quite significant. The discharge head supports the pump below, the motor above, while providing both a discharge in most cases and all cases and sealing. And realizing the discharge is seeing full pressure, so shaft sealing can be a little tricky. That head can be either cast iron or fabricated steel. The colling and shafting are on longer units shipped loose. Up to about 25 feet you can specify factory assembly, and it'll just arrive that way, usually on wood that's giving it some support. The bowl assembly, which is the pumps in their impellers, each one is called a bowl, and they're assembled from an inlet piece and impellers, and they're all mounted on a common shaft. At the bottom of this is a typical, the bowl can be water lubed, and in most municipal applications, because water is a good lubrication. And the bearings are like on ski boat prop shafts, water lubricated. Now the inlets. Inlets are more often of the bell type, so it's an inlet bell, nice and smooth, with a strainer on it to keep dead bodies and whatever from going into the pump. Now, if it's to be installed into a water well, then the inlet will be threaded, and there'll be what they call a tailpipe, which puts the screen, and the screen is done as a narrow cone at the end of a piece of pipe. And that pipe puts it in the center of the well screen in the well. Here's pictures on the top shelf here. You can see different basket strainers all ready to be put on pump to manufacture. And below that, cone type strainers. Moving up now, back again. The bowl assembly, and you can, bottom, it has two different inlets. It's sort of cut in half. On the right-hand side is, we're talking about the threaded piece for a well, and on the left side is the suction bell, which you see if you're pumping out of a sump or whatever. The interesting thing is, you see how these stay, the impellers are held on. Second item down on the left, impeller collet. What the collet is a wedge, and that wedge holds the impeller to the shaft. The manufacturer had a case where they actually, to meet a petroleum standard, machined it so that it is held with a ring both up and down and from the side, mechanically fit. That met that standard, therefore they could sell lots of these pumps, and did, into the petroleum industry. But the collet, to me, is a better system. There's nothing wrong with it. For municipal use, that's the way to go. The manufacturers, the diameter of the bowl is usually intended to just fit into a well. And so it will have a size. And the bowl also, not everybody, but most manufacturers will designate it based on flow capacity, like LMH, which means a low capacity bowl, a medium capacity bowl, or high capacity, which can be combined with impellers of different flow capacities as well, such as LC, MC, and HC, low capacity, medium capacity, high capacity impeller. Now, say different people have their own way, but most of them will follow this approach. So when you see like an M14HC, that means it's a 14-inch medium capacity bowl with a high capacity impeller. And the total number of stages, like this on the left here is only showing 2, the total number of stages will usually be given by a dash followed by the number. Like an M14HC10 will have 10 stages. Note that a smaller capacity bowl and impeller may be efficient to meet your design conditions, but require a whole bunch of stages. If you do that, you'll end up with a relatively steep head curve. The more stages, the steeper the curve. Conversely, a larger low-capacity bowl and impeller may also efficiently meet the conditions. So what we're talking about, maybe in the first case, you've got a 10-inch pump, and you've got, I'm picking numbers here, but maybe 5 stages. So that's, moderately steep curve. Then we go to a 12-inch bowl, and maybe we can cut back to 3 stages. That curve will be flatter. The fewer stages, the flatter the curve is. And we're talking about collets. This shows how they actually build it. The pump shaft is put on a rack, and at the right-hand side, top right-hand corner, the shaft is actually physically held relative to the inlet of the pump. Then they will bolt on a bowl, slide an impeller in all the way, and then take the collet. You can see the little bronze thing there on the shaft up to the right. And the collet driver, that thing down on the left, just to the left of the wooden block, is actually a weight, and that one end of it is designed to hit the collet. So the guy will simply take that, flip it on the other side of the wooden block, and just go bang, 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 and it drives the collet in, and that's it. The other side, if they have to pull apart, they will pull the shaft out as far as it'll go, which is not much, pull it out, and then hit it with the outer part, which is designed to miss the collet and drive the impeller off. And you just keep building them up in stages. And there's the collet, you can see it has a split on it, and it just slides down the shaft and is driven into the impeller. How many stages can you have? The answer to that is lots. Here we have a whole bunch of them. Here we have a whole bunch of them, and that is my wife with her safety glasses and her safety sandals on. Now, looking at the typical pump curve, and here's an M14HC, as we were talking about, and the efficiency is pretty steady once you get up to a certain number. And this thing will show you, like if you have one stage, you've got to knock single stage by itself, take 2% off the figures here. 2 stages, take 1. 3 and beyond, what you see in here is what you get. And basically what happens is the next one, is you add stages, the head multiplies. Like here, we started off shows one stage at a shut-off head of 120 feet with the trim we have. 10 stages would be 1,200 feet. They simply, the heads add up as you add stages. The capacity is identical. The efficiencies, once you get beyond 2, are identical with this particular pump. You have a thrust constant down here. The thrust constant is used to calculate the thrust that that the motor will see, the down thrust created by the bowl assembly. And at the bottom, it's got a little footnote of performance based on cast iron enameled bowls, almost like a enamel sink, and a bronze impeller. And different materials have slightly different efficiency corrections, okay? Now, moving up from the bowl assembly, and you can see the impellers can be trimmed just like they would with any pump. You can see the NPSH required, which doesn't vary as the stages, and you can see the horsepower required for a single stage, like this thing peaks out at maybe 50 horse, something like that. And if you had 10 stages, you'd have 500 horse required to drive the thing, okay? Now, moving right along, column and shafting. Column pipe is either threaded or flanged with a spider bearing retainer that fits in to support the shaft with sleeve guide bearings. For 2-pole motors, i.e. 3,600 RPM, less whatever slip, the column comes in 5-foot sections with bearings at each joint. So the bearings are 5 feet apart because they're running at higher speed. At 1,800 RPM or lower, then you can have every 10 foot. In other words, they're 10-foot lengths of pipe. The shaft is supported every 10 feet. And that applies from 1,800 RPM 4-pole motor from there on, slower and slower and slower. You can get enclosed oil lube line shafting available, but mostly you see that in industry and used as drainage pumps. Most water applications, the line shaft is simply lubricated by the product itself. It's very much like a jet boat or a ski boat shaft. If the length of column and shafting exceeds 50 feet, then shaft lubrication at startup becomes an issue. In other words, it may take a bit of time before water gets up and those bearings are running dry, and they don't like to run dry for very long. We're talking seconds. If that's the case, then that the water level and the shafting is 50 feet or more, then you talk about preloading, okay, of simply dripping water with a timer down that shaft and everything else. Now, if you're in that kind of a situation, nowadays they have synthetic shaft guide bearings that are capable of operating dry for up to a minute. Well, when you fire up the pump, even with a soft start or whatever, a minute is a long time. So at that point, you don't have to worry about pre-lubing. But that's at one time in history that was a very important thing. Threaded column or threaded impeller shafting. Well, somewhat rare. One could always confirm if a pump utilizes an impeller that is threaded on the pump shaft rather than slip on or key. Virtually all vertical pumps have threaded shaft connections. Threaded impellers and shafting connections can cause, we went through this before, that this can be an issue. Now, vertical turbine pump motors are available with non-reverse ratchets, but these are primarily intended for deep well applications. People say, oh, well, it's in case the motor starts backwards. Yes, it will prevent damage from that. But the actual application was the fact that if you have a deep well and you stop the pump, the water will start going down the well and turbine it. So it's spinning. The shaft is spinning after you've shut it off, spinning backwards. What happens is the upper bearings go dry and the shaft is still spinning and they can burn out. So the idea of the non-reverse ratchet was to actually prevent that by preventing the shaft from turning backwards. Okay, now if a pump with thread impeller or threaded shafting is turbining backwards by reverse flow, some people said, oh my God, it'll unscrew the shaft. No, it doesn't. When the pump is running, the shaft tightens, and when it's turbining like this, it also tightens. The only time you can get into a problem is if a pump with threaded impeller or shafting is rapidly slowed. like a short speed industrial, or pardon me, adjustable speed ramp down time, where it slows the motor quite quickly. The inertia of flow plus the rotating assembly itself can cause threaded connections to partially unthread. Then when the pump is restarted, the connections will quickly rethread, bottom out, you get a heck of a bang, and it can cause damage given a chance. Now the discharge heads are three major functions: supporting the drive motor, providing the sealing gland or mechanical seal as the shaft exits the head, and terminating supporting the pump column pipe, bowl assembly, and intake. Two most important factors are the base of the head and the height of the motor stand. If the discharge head will be used with an inlet barrel, then the base should simulate a flange connection, it has to bolt onto the barrel. And while a low motor stand allows a more rigid head, access to the shaft sealing gland or mechanical seal is limited. An adjustable solid shaft motor coupling is impractical. We'll get into later the type of motor you're using and these adjustable solid shaft motor couplings, okay? And here's showing illustrations of them. A cast head on the left, and you can see the base of this one has obviously been set up for bolting onto a inlet can or barrel. You can see the in this case is packing. You see the packing gland, and you see the discharge to the right. The motor would be on the top. Fabricated, very similar, but it is fabricated. Okay. Now, if you're pumping out of an inlet barrel, classically the inlet to that barrel, there's an inlet right on the barrel itself, so flow comes into the barrel and then goes out through a head like this. But you also can get what they call a T-style discharge head, which has an inlet and gets flow into the barrel. Now there's a picture of it here, okay? You can see inflow is bigger than outflow. Your incoming line, you want to boost pressure. Incoming line comes in and discharge. See the arrows going down from the vertical? That goes down into the can, and you can see just to the either side of that arrow, you can see where the bolts are that bolt it to the inlet can or barrel. Then the pump is the arrows coming up, and it discharges off to the left. Then the barrel does not have to have any inlet connection at all. Now, how they bolt to that O-ring, yes, they're designed. You can do it with a gasket, but a better option is to utilize a dynamic sealing O-ring with a machine groove, so that the connection actually is sealed using an O-ring. And that's an interesting approach, but a very good approach. Now, talking about T-discharge head, here again is my charming wife standing beside one, and you can see the inlet has been covered with plywood to keep the birds out. Inlet on the right, discharge on the left, and the motor stand, which has guards so people don't stick their fingers in, and the motor would then set up top at about her head height, okay? Now the motors themselves, there are two different approaches you can take to the motors, either solid shaft or hollow shaft. Realize these are not your typical motor. They are designed to take that high axial thrust, okay? Solid shaft, the motor takes all of it, and the shaft just goes up. In a hollow shaft, the motor shaft is actually hollow, and the pump shaft has an extension that carries through that hollow, and then at the top, there's a coupling plate with a nut you can use to adjust the pump down below, and there you are. It's called a head shaft, that shaft that extends on and usually comes with the pump. Now, hollow shaft motors, again, have their roots in deep well pumping and can be provided with several things. One of the problems, as we mentioned, is that if the thing starts up the wrong direction, or for some situation there is an upthrust on that pump, then you can have issues. So to prevent the shafts from unthreading, whatever, the basic thing is a self-release coupling. The coupling, there's little, you can see where it says disengaged, you can see the pin there. So if the motor starts backwards or there's any upthrust on the pump, that causes the shaft to extend up. It simply uncouples. Now the problem is it comes down, and if anything's spinning, which it is, it's just a pin engaging, and bang, it's going to come down fairly rough. But that is the basic. Next thing is, if you've got a situation where the pump can, in theory, have upthrust, and that hydraulic, where the inlet pressure is acting on a shaft or gland, it can occur in booster applications particularly. You can bolt down the self-release coupling. It no longer will release, and you can see and they also at that point will lock the bearing at the bottom. This provides no reverse rotation protection, and the only thing that's taking that upthrust, you see where it says lock screw? That's it. I have heard of people drilling and putting in 2 or 3 of those to deal with it. Now, the classic way to prevent reverse rotation from unthreading shaft is to use an unreverse ratchet. Okay, it will only allow the motor to spin one direction. And as I say, it was originally designed to prevent damage in well pumps beyond that 50 feet, where the spinning shaft would burn out bearings. Now, non-reverse ratchets can be quite noisy when the motor is operating at lower speeds. So the moment you start talking, I want a soft starter, which has soft stop, we'll get to those much later, or an adjustable speed drive, these things can be quite noisy at low speed. The balls tend to fall in, and they're whatever. Solid shaft. It's interesting. A lot of municipalities do use solid shaft, and that's simply because of their roots in deep wells. Industry tends to go with solid shaft, and I must admit, you need to look at what your actual application is and what's good, never mind what has been traditional. And certainly I would recommend going solid shaft. It can readily absorb hydraulic upthrust quite a bit. It also does not make noise when you're dealing with soft starts and adjustable speed drives. Okay, and while you can get solid shaft motors with a ratchet, as I say, I don't like them. Now, what you have to do, because the shaft does not extend through the motor and adjust it at the top, what it does is you have to have an adjustable coupling between the motor and pump shafts under the motor. Now, there's an unspacer type or a spacer type. And much like dealing with, we were talking about spacer couplings with frame mount pumps, end suction pumps, the advantage of the spacer coupling is you can get at the packing or mechanical seal and remove that mechanical seal without having to pull the motor. So a adjustable spacer coupling, in my humble opinion, is the way to go. Thrust ratings. The top bearing of a motor, be it vertical or solid shaft, provides the down thrust capability, and each vertical motor will have a thrust rating based on a 1-year L10 minimum bearing life, which is by definition number of hours that 90% of the bearings will complete before fatigue failure. Now you say, why can't I have bearings that never fail? Because it just seems to be that way, that you can have brand new bearings that'll fail. So based on averages, the thrust rating normally based on L10, which equates to a 5-year average bearing life, number of hours that 50% of bearings, okay? And you can get optional thrust bearings, typical 175%, to increase thrust load. Now, pump down thrust, remember that thrust constant? Pump down thrust is calculated by multiplying the specific bull thrust constant, remember it's 12.5 for the example we had, by pump head plus the weighting impellers and everything else. Often ignored with close coupled pumps. Several hundred feet down in a well, yes, the shafting is heavy. Close coupled, it gets lost in the shuffle. And the spec that I would typically use, motor thrust by momentary 30% upthrust, that is the standard design for motors, upthrust capability, and shall also provide a minimum bearing life of at least 44,000 hours and an average life of at least 220,000 hours of continued pump design condition down thrust, which means the bearing has to be above normal design by 1.75. And because you can get this extra high thrust bearing at 175, that usually is not a problem for the manufacturer. You get an upgraded bearing, which means you get considerably upgraded bearing life. Now here's a picture of motors. Um, the three on the right on the ground, you can see the little hats on the top, which even on the solid shaft, they'll do it that way because of manufacturing advantages, but they could very well be solid shaft. If they were hollow, you pop that thing off and there you do your adjustment. The one on the left is definitely solid shaft, as is the big one that stands there. You got no access to the top. You don't need knives. They are being used. They are vertical solid shaft motors and would be used with adjustable couplings. And just for the heck of it, in the background, you can see kind of rusty. They haven't been coated yet. They'll be sandblasted and everything else. You can see inlet barrels. They're sitting upside down, inlet barrels. Okay. Now let's get into, not physically, inlet barrels. When provided with a conventional discharge head having a lower flange type connection, a close-held vertical turbine pump can use an inlet barrel. It doesn't know that it's not in a lake or whatever. And you have an inlet connection at least 2 bell diameters above the inlet bell, and water comes in there, goes down, and then is pumped up by the pump itself. You see the basket there, single stage in this case, up to the top, and the discharge head off to the right. If you go with the T head, like the drawing on the right, you don't need to worry about any inlet on the barrel itself. It is also strongly suggested, if you're over 3,000 gallon per minute, that you put in guide vanes with angle tops. Angle tops make it easy to drop the pump down, and those vanes are literally to take out any swirling that may develop in the water dropping down to the inlet. Okay? Now, the little trick, the exception that the engineer knows. While rather unusual, it is possible to pipe directly into the inlet of a vertical turbine pump, usually accomplished by using a bowl assembly with threaded inlet and adapter pipe. Okay, but you can hook up direct. Inlet flow should be as even as possible to prevent vortexing and uneven impeller loading. A large diameter head will get into design later on with straight branches is suggested, so the flow is sent straight into the pump itself. The manufacturer should be made aware of what you're trying to do, because many vertical turbine pump assemblies leak a little, but the way they're installed, nobody knows. If they're in a well or an inlet barrel, you don't see it, you don't worry about it. But here, where they are going to be exposed, very often O-ringed, so that there is no leakage at all. What that does is allow you to have a booster pump that doesn't need an inlet barrel or can. Both those terms are used. Now again, a war story. There was a pump station, and this is shown before any action was taken, that had 2 50-horse vertical turbine pumps. You can see the gray motors on the right, plus an engine-driven pump, which on the left, that's the gearhead and the engine beyond view, installed within inlet barrels. It was decided to upgrade to 3 200-horse motor-driven pumps, but significantly larger inlet barrels would be required and be nearly impossible to fit them within the existing station. Accordingly, a new station was planned, After reviewing the existing station and the proposed new pumps, concluded that by omitting new inlet barrels and utilizing dry inlet connections, the existing station could be retained, would not have to be destroyed and a completely new one built. This was a significant cost saving to the client. Vertical turbine pump factors, performance curve, as I say, inherently steep because of the number of stages, but you can play games with stages. Now, you can get vertical turbines with few stages to meet the specification. Shutoff head shall not exceed 140% of rated head. Pump shall furnish not less than 150% rated capacity. That's essentially the NFPA 20 spec, the way it is. But if you want a steep head curve, then you change that to shutoff head shall be in excess of 140% of shutoff head. And you throw in always calculated column and discharge head friction losses shall be provided for in the bowl impeller suggestion. Flow range should be within acceptable standards. We got into that earlier. Plus or minus 50% is always a good rule. Inlet, not a problem. NPSH required. You don't normally see this with water, but if you do, and a trick that's done with petroleum is we're talking about looking at the bowls and impellers. Very often you can, let's say you've designed your pump and here's the number of stages and what I want. Very often you can look at the thing and say, if I go to a high capacity inlet stage, it will have a lower NPSH. So you can use that impeller for just, or even bolus, whatever, that will give you this low NPSH and enough capacity for the first stage only. Once you get past that, the second stage is seeing a nicely pressurized inlet and cavitation is a non-issue, okay? And we mentioned about rotation with vertical turbine pumps, and I pumping out of a well, and I have there was a classic example where they kept getting motor overloads, and what it turns out is there's a certain period in the operation in the middle of the night where the inlet flow was quite high when the pumps were down, and it was swirling opposite what the pump was turning, and they would overload, okay? Venting must ensure the pump head is properly vented, and also that the inlet barrel is vented to prevent pipe dry running of the pump. These things are using, most cases, water lubricated bearings. You run out of water, you start counting how many seconds it is before the pump destroys itself. Radial thrust is almost non-existent, so it pretty much a non deal. Axial thrust, quite apparent and dealt with by motor. The comment being I've heard is that it's one of the, actually an advantage with vertical turbines because that high thrust of the pump tends to stretch or pull down on the shaft, which prevents whipping. So on rare occasions, if you get too much axial thrust and need to bring it back, you can actually take impellers that will accept a rear wear ring and vented impeller hub, like an end suction closed impeller, which will cut back on the axial thrust. The footprint of vertical turbines, of course, is very compact. Now here you see a bunch of impellers. The one on the left here hasn't been machined yet, but it has the hub at the back suitable for machining. So you'd have a wear ring, normally on all of them, a wear ring at the bottom after that's been machined, whatever, and one at the top where the fingers are, okay? Now, on the right-hand drawing down the bottom, the outer impellers on either side are the typical enclosed vertical turbine impellers that are so often used, and these ones don't have provision for a hub like that other one for a back wear ring. And here you can get semi-open impellers, and again, they're very good for efficiency. They do have high down thrust, but they are good with sand. In fact, a lot of well drillers used to use them, and they'd set them up so that these are shown upside down. They'd set them up so that it's almost like a recessed impeller, and they could pump sand. One thing is, if you're ever doing it, well drillers know, if you're pumping sand with a vertical turbine, for God's sakes, don't stop it until the water coming out is clear, because what happens is if you stop it while you're still pumping sand, all the sand will go down and collect at the bottom around the impellers, and you may not be able to start it again, and you have to pull the pump to clear out all the sand. Servicing. They are more complex and harder to install and more difficult to service than horizontal pumps, but they do have a smaller imprint, do have better efficiency, and you can play games with the curve and things like that. They have inherently, they tend towards steeper head curves. That is an advantage where you are pumping to an open discharge, for example, pumping to a reservoir or whatever. That steepness will allow you to stay within a design point much closer than you would with a flat curve. Okay? Where the water supply is below the pumping floor, short coupled vertical turbine pumps are a natural, like you're pumping out a reservoir, put the pumps on the reservoir. Where higher inlet or discharge pressures are involved, the booster configuration using a can works well. In other words, you're trying to boost pressure, and pumps just add to it. So this gives the vertical turbine pump whatever inlet pressure you got, let's say 100 psi, to which it may be add 50 psi, and you got 150 psi discharge. An inlet, as we said before, either into the barrel or use a T-head like we've shown here. So in general, vertical turbine pumps can be assembled into many varied configurations. Here's the short coupled. Is relative, but standard 25 feet, whatever. Pumping out of the ocean or a dock on a lake or some whatever. Booster means that the inlet is provided with a can, occasionally direct. Okay, but use caution if you do go direct. Well pump, yes, the bowl assembly and inlet are down in a well. How deep? Several hundred feet is not uncommon at all, and I've heard of several thousand feet. Now the last option is submersible, essentially a close coupled bowl assembly with an inlet piece that also has provision for an integral submersible motor. Axial thrust is then seen as a compressive load into the integral motor's lower thrust bearing. Let's talk some more about submersible well pumps. Say they're vertical turbines with the motor at the opposite end. Long lengths of shafting are unnecessary, therefore pump removal is simplified and well straightness much less critical. The straightness of a well can be a problem with the shafting on a vertical turbine pump if it has to bend a bit. Significant thing is the discharge check valve is close to the pump, so there's no surging of the well on pump startup or shutdown. When you start, particularly, let's take the classic example of constant speed. If you start up a deep well pump, to begin with, the pump bowl assembly is not seeing any discharge head, so it tends to run out and you're drawing in quite quickly. Then when you shut it down, the column of water wants to go back down into the well. And that then you're flowing out through the well screen and the sand that's been developed around that. Interesting thing, in Europe, it's not uncommon to put check valves on the inlet of a vertical turbine down in the well below the bowl assembly. In North America, it's virtually banned by most manufacturers. But with submersibles, it's a non-issue because the head stays there. The check valve is down close to the pump. Submersible well pump motor inevitably operate at two-pull speeds, i.e. 3,600 RPM less a little bit of slip, to keep the motor size as small as possible. And noise is obviously a non-concern because they're way down there. Within acceptable parameters, submersible well pump motors operate extremely well with adjustable speed drives. They like it. A significant feature available with submersible well pump motors with adjustable speed drives is the ability to incorporate level control and modulate pump speed to maintain a minimum well drawdown. What that means, if you're pumping out of a well, normally with a straight constant speed motor, you may have a situation where you can overpump the well, in which case typically there's an alarm and the pump is shut off and they've got to throttle the pump a little bit and da-da-da-da-da-da. With adjustable speed, you can actually set up, and we'll get into this, you can set up a level control where at a certain minimum point, it will actually start changing the pump speed, allowing you to take whatever the well is capable of delivering without overpumping it and having to shut it off. Now, there's an argument that all submersible well pump motors should be three-phase and operating from an adjustable speed drive. One, the adjustable speed drive because of this level control thing. Also, you get rid of all the, and we'll get into motors later, all the, dare I use the expression, crap that comes with single-phase power supplies. The drive, an adjustable speed drive, can act as a phase converter. Even if you want to go simple on-off operation, it can play phase converter. Now, check valves. Discharge check valve can be utilized to ensure column separation, which can lead to water hammer cannot occur. Check valve is down at the bottom. You've got lots of head. When the pump starts up, it sees that shutoff head, starts it nice and smooth. When they're not built into the pump, it is common, as small units have, we'll get to that in a second, it is common to have a check valve one pipe length, about 20 feet, above the pump to help dissipate shock waves. In other words, if the pump stops quickly, the checker will go whomp, and any shock has about 20 feet to dissipate itself before it hits the pump. Now, pancake pumps. Lunchtime. Now, pancake pumps, small submersibles, typically starting at about 4-inch, they can even get 3-inch diameter for 3-inch wells, believe it or not. And they are radial flow, so they're low specific speed pumps. At one time, they were plastic molded impellers and diffusers were the way they did it, contained within a bronze or stainless steel sleeve. Okay, now what they've done, and to my knowledge, Grundfos was the one that started it, fabricated from stamped stainless, believe it or not. Everything you see in this picture is stainless. Most of it being stamped. There's a little bit at the bottom, the motor mount is likely cast, but everything else is stamped out of stainless. The tooling is something else to do that, but there you are. Grundfos is the most common name. There is an Italian company that provides brand labeled. In other words, if you're brand X, then they will provide it with brand X on the boxes, and you can claim it's yours even though it isn't. Most of them are intended to fit within 4-inch or larger wells and have an integral plate type discharge check valve. If you look at just above, right at the very last piece on the row going up, just above that top impeller, you see there's a little plate there, and that is the check valve. You can get fabricated stainless steel submersible pumps up to about 80 gallons a minute, which is 5 liters. And while larger fabricated stainless steel submersible pumps are available with higher specific speed, i.e. more efficient designs, they're generally not as efficient as submersible pumps using enameled cast iron, bronze fitted, or stainless steel fitted vertical turbine pump bowl assemblies. So I would, in these small sizes, 4-inch, yes, they're the way to go. Beyond that, go back to conventional vertical turbines. Now you can use small submersible well pumps, can be adopted for a number of things, and actually insert them in a case, in a carrier pipe. This particular design was actually intended for handling leachate out of garbage dumps, but can also be used for water pumping from a lake or pond. And you just discharge pipe, just roll the pump down there, and away you go. And I've mentioned the company in case you want to go that route and get in touch with them. Now, another thing you can do with small submersible well pumps, or any size really, is can them or mount them within a short section of pipe. The advantage of this approach are, number one, unaffected the pump itself by inlet pressure. Number two, there is no packing or mechanical seal. There is no shaft going outside of the unit. They work best when the pump can be mounted vertical, but that somewhat limits how far you can go in size. Larger horizontal can submersible pumps are available, but they're somewhat problematic, and I would avoid them if you can. The most difficult part of building a can submersible pump is actually sealing the pump power cables as they leave the pressure vessel. Now here is an example. This was done by somebody, and they've got canned submersible pumps inside each one of these blue cans. What happened was they showed the wires coming through with a seal, but the pump supplier didn't know how to seal it. So initially, this is how it was sitting in the field, and they're sort of hoping that by some miracle it would be solved. I told the manufacturer or the pump supplier how to seal them, and then you see the pictures of them actually being sealed. And you can see that sort of curvy thing coming out each one is where the leads are, the 4 wires that go into for powering the thing. You can see air releases are extended out there, okay? And again, war story. Decades ago, University of Alberta in Calgary wanted a pump for a simulated seafloor petroleum process to circulate seawater at a few hundred US gallon per minute and about 20-pound differential. but at an ambient pressure of 1500 psi, in other words, coming in at 1500 and discharging at 1520. Provided them with a submersible well pump mounted within a pressure vessel with high pressure Victaulic end couplings. You see these couplings here at the bottom with 4 bolts instead of the typical 2. These are designed for well application. They're like 2500, 3000 psi rated. And you can see there's the pump, just a single stage submersible motor at the bottom. And you can see the top part that dropped in and was bolted. It was a bit radical, but we found out several years later that it was working just fine, and the university were happy campers. Now, a variation of pancake submersible well pumps is vertical multi-stage, which is blending the pancake. Relatively small pumps, the largest having a flow rate of about 500 gallons a minute. They make ideal jockey pumps, have nice deep head curves, along with the pressure relief valve or with a hydropneumatic tank or multiple tanks. The motor actually, believe it or not, is not a high thrust motor. It's a typical motor with a coupling, and because these are pretty small animals. Now, if you got very low flow demand, you run the risk of overheating the pump. So recirculation bypass temperature sensor can be specified, and on reaching about 60 degrees, solenoid will open and discharge flow to a reservoir or wherever. Ensures the pump will not be damaged by overheating. Once open, it remains open for about 5 minutes. If you shut the discharge off and let these things run, they will overheat, they will boil, and they will destroy themselves. Now, if flow demand is low, measured by a flow meter of some sort, jockey pump flow meter, the pump will be stopped. The pump will then remain stopped. This is another option until water is taken from hydropneumatic tanks. So basically what it is, you're pumping, and these work nicely with big pumps. But what do you do at very low flows? And there's an old rule of thumb, always assume with water that the flow rate demand will go to 0 at some point, unless you're pumping into a reservoir or whatever. Therefore, you take one of these as a little jockey pump to handle low flows, and you pump into a hydropneumatic tank, which almost like a reservoir. When the tank pressure is up, they turn off. When the tank pressure drops, the pump turns on. Okay, fine. Let's talk a little bit about hydropneumatic tanks. Now, that's the advantage we mentioned about the flow rates are down to 0, the advantages of that. You see them in domestic systems a lot. You can, with these type of tanks, you can multiply them. Not uncommon, well, I shouldn't say not uncommon, rather uncommon, but you can have, say, 20 tanks to give you a fairly significant capacity, okay? Now, a modern hydropneumatic tank has an internal diaphragm containing air that has been pre-charged to the minimum cyclic pressure. If you're going to run 20/40, it'll be pre-charged at 20. If you're going to run 30/50, in other words, pump on at 30, turn off at 50, then you'll pre-charge it to 30, okay? Diaphragm prevents air absorption by the water. If you did not have that diaphragm in there, water will eventually absorb the air, and you'll end up to the point where there is no tank, and the pump will just go bing, bing. You can turn on and off, turn on and off, turn on and off, because there is no useful volume, okay? The actual draw-off live volume is a function of the spread between on and off pressures, as well as the magnitude of those pressures. Okay, now this shows how the tank works. And I'm going to flip to a graph in a minute. And it tells you to use this graph, start at 0 water in the tank, empty tank, and low pressure, 30 psi, and then find the volume at high pressure. Okay, then multiply the actual tank size by the percentage to get a useful draw-off volume. Okay, for example, and let's go to this, let's say you're 30 to 50 psi. Okay, we start where 0, go up to 30 psi, come over to the line that started from 0. Okay, you're roughly, what, maybe 7%, something like that. At 50 psi, you're up to about 15%, so you're getting about 7.5 between the two. Okay, why do I show 50? 30% draw off. Okay. Well, sometimes a mistake is a good thing. We start at 0, we go to 30, which is about 7.5. At 50 psi, that line comes up to about 15. Okay, I'm going to stop it at this point. My apology, this thing can be a little confusing. So if we go to zero volume, in other words, on the left vertical of the curve, start at 0 and move over to your low pressure, which is 30 psi. Okay? Take that curve. So we're starting with nothing in the tank because it's been pre-charged to 30 psi. As we put water in, take that line right at 30 and start moving up until you hit 50 psi. So where that line contacts 50 psi, you're about 33%. Okay, so that's the volume. Like it was a 100-gallon hydropneumatic tank with that pre-charging, you'd get about 33 gallons of useful volume between 30 and 50 psi. Now, if we go say 80, 100, again a difference of 20 psi. If we go to 80, 100, if we're starting at 80, follow that line from 0 down in the left corner, horizontally along to 80. Now take that curve there and follow it up to 100, and you're about 17 and a half. So you've about half the useful volume by going from 30, 50 to 80, 100, okay? So what comes out of that is it's really an advantage to have the hydropneumatic tanks, if you can do it, mounted at a spot in your system where the heads will be relatively low. For example, this system, by the way, will work very well in commercial high-rise buildings. And the tanks can be installed, if they can be installed, which usually can, on the upper floor of the building. And then the basement pumps, operated for cycle operation at low flows. This can be very efficient because there's long periods of time when the pumps aren't running at all because the demand of the building is very low. Same thing in a municipal system. If you pick the high spot in the municipal system, or in a better example, municipal system, yes, or trailer park development, whatever. Pick the high spot in the system to put your hydropneumatic tanks to make the jockey pump happy. Therefore, you will get more draw out of what you've got. Now, there was previously, you could see a spec for a pump or tank that I would recommend. And now what we have here, sort of a guideline for applying water pumps and whatever. Open discharge to a reservoir or closed discharge, pressure system variable flow. Well source, reservoir source, pressure source, and it goes down what the options are, like well source, submersible at the bottom end, vertical turbine Francis type at the upper end, up to about 230 horse is the limit. Beyond that, call me. That's the limit of our Franklin motor, which is 200 horse with a 1.15 continuous service factor. And all these, and the blue is the control system they're used. And again, at the bottom, it's got here showing what all those mean. So type of pump, whatever, St. Close system, that helps you. So at that point, I'm done with Kinetic pumps and hope you do have a good day and go on to the next important slide.